In this lecture, we want to discuss about equilibrium. Definition. If a body is at rest or moving with uniform velocity under the action of many forces, and as a result, there is no change in its translational motion as well as in its rotational motion, then the body is in the state of equilibrium. Translational motion means the body moves along a straight line. For example, bullet fired from a gun. Rotational motion means the motion of the body in a circular path around some fixed point. Please note there are two types of equilibrium. First, static equilibrium. Second, dynamic equilibrium. As far as the static equilibrium is concerned, if a body is at rest under the action of many forces, then it is said to be in the static equilibrium. In static equilibrium, please note that there is zero velocity and zero acceleration of the body. For example, a book is on the table. In this case, when the book is on the table, the weight of the book is balanced out by the normal force acting on the book from the surface of the table, because both forces balance each other. So in such case, book is at rest under the action of these two forces. So this is a very simple example of static equilibrium. The second type is dynamic equilibrium. As for its definition is, if a body is moving with uniform velocity, then we say that the body is in dynamic equilibrium. In dynamic equilibrium, there is velocity, but zero acceleration of the body. For example, a car moving with uniform velocity. But dynamic equilibrium has further two types. First, dynamic translational equilibrium. Second, dynamic rotational equilibrium. If a body is moving with uniform linear velocity, then the body is in dynamic translational equilibrium. For example, a paratrooper falling down with constant velocity due to the force associated with air resistance is the same as that of the gravitational force. Gravitational force means weight of the paratrooper. So when in the case air resistance balanced by the weight of the paratrooper falling down with constant velocity. And the next type is dynamic rotational equilibrium. If a body is moving with uniform angular velocity, then the body is in dynamic rotational equilibrium. For example, when we want to play the CD player, then in that case, when we put the compact disc, I mean CD, inside the CD player, then the CD is rotating with constant angular velocity. So in that case, we have dynamic rotational equilibrium case, because the CD player inside the CD disc inside the CD player is rotating with the constant angular velocity. Now there are two conditions for a body to be in equilibrium. The first one is called first condition of equilibrium, which is happened when the vector sum of all forces acting on any body is zero. So mathematically we can write F net equals F1 plus F2 plus F3 up to Fn must be equal to zero, which we can also write in the summation form. You can see here, this symbol is a symbol of summation, where I starts from 1 and goes up to n. So if I put I1, then it means I'm talking about F1. Plus, now when I put I2, then it means I'm talking about F2, and so on up to Fn. So this must be equal to 0. So have a look this figure where we have so many forces in XY plane, and we wanna sum up all of them and wanna look the resultant force. So in that case, when we follow the, we have different methods to sum up them. The first one, just to keep the head to tail rule, and by putting the tail of the second on the head of the first force vector and keeping this method up to the last force, then ultimately we will get the resultant of all forces. And the second is, if we resolve each and every force in its components, then finally when we sum up the summation of when we take the summation of the x component of all forces and summation of y component of all forces, as you can see here mathematically, which we can be written like f of xi plus summation f of yj equals to 0, then finally if we get the resultant of all forces equal to 0, then it means the first condition is satisfied. So this is how we can do in this figure B, and you can see ultimately after doing the head to tail rule, apply the head to tail rule on all forces, finally we get the null vector. You see F5 comes up to the origin. It means it comes up to the 0, means null vector. So that is how we can sum up all of them and say, okay, vector sum of all forces acting on any body is 0. So the first condition of equilibrium is satisfied. This means that there is no linear acceleration and body is in translational equilibrium. And as for the second condition of equilibrium is concerned, when the vector sum of all torques acting on any body is 0, then we say that the second condition of equilibrium is satisfied. Mathematically, we can write that sum of all torques acting on any body, tau 1 plus tau 2 plus tau 3 up to tau n, must be equal to 0. So then we can say that second condition of equilibrium is satisfied, which further can be written in the summation form, as I have already discussed in the case of sum of all forces on the last slide. So this must be equal to 0. Here you can also note that the sum of all torque in the clockwise direction must be equal to sum of all torque in the anti-clockwise direction. And if you by convention take the sum of all torque anti-clockwise in the anti-clockwise direction minus, then by conventionally you must take sum of all torques in the clockwise direction positive. So by doing this, you can sum up both and finally you get 0. So the second condition of equilibrium is satisfied. This means that there is no angular acceleration and the body is in rotational equilibrium. Dear students, that's all for the today's lecture. In next lecture, I'll discuss further the different state of equilibrium. Thank you so much for watching.